So originally my title was something like Symmetries of Weight 6 Polylogs, and I think probably talking about that is like too much for the moment. I will focus more on the story of depth reductions in weight 4 first. And then maybe at the end I'll mention what's going on in weight 6. But it makes more sense to start with weight 4, and this is maybe like supposed to be a continuation of what Clement was talking about. So we'll start with a little recap of the notation and the setup and things. So the multiple polylog, we can try to follow the same notation. Indices were n1 through to nr, or z1 through to zr, is, as an analytic function, just the sum of 1 less than or equal to k1 less than k2 less than or equal less than kr, of z1 to the k1 to the zr to the kr, over k1 to the n1 to the kr to the nr. So far we've spent most of the time talking about the depth 1 case, the classical polylogs, whereas Daniel was talking about the higher depth ones. So these are the multiple polylog functions we are interested in. Notation as usual is the depth of this function is the number of indices. And the weight, and sometimes just abbreviated as WT, is the sum of the indices. As analytic functions, they are these things. But in Clement's mini course, we had the explanation of how these things can be lifted to motivic objects. So we have a category of mixed state motives over some field, work over a number field if you want. And by the functor omega, going from mixed state motives to finite dimensional Q vector spaces. And in particular, from the reconstruction theorem, this category is equivalent to category of representations of automorphisms of this functor. Where this thing gets called the motivic Galois group, and as Clement explained from the weight filtration and the weight grading of omega, this decomposes as semi-direct product of the multiplicative group and some group. And it was on the regular functions of this pro-unipotent part that we defined the motivic polylogarithms. So the algebra and the co-algebra. So the last thing of the recap. Motivic Hopf algebra was regular functions on the pro-unipotent part of the motivic Galois group, and the co-algebra is the quotient of the Hopf algebra modulo products. Then by these matrix coefficients, I explained how to define the motivic version of the logarithm and the classical polylogs, and mentioned you can do the same for the higher depth polylogs. We have the motivic version of the log living in the weight 1 piece. Generally, the motivic version of the weight n depth 1 polylog, living in the weight n piece, and completely generally motivic version of the depth r polylog living in the weight whatever the sum of these indices is piece. And then by projecting all of those to the Lie coalgebra, you get the polylogs modulo products. You get and as part of Gondrov's sweeping family of conjectures, the expectation is the motivic Lie coalgebra is generated by motives of polygons. Still, that's a step we don't know. So maybe just for the sake of introducing some notation and kind of alluding to things from yesterday, we expect that the motivic Lie coalgebra in this setting is generated by polylogs. So what I want to do today is try to explain some of the ideas of depth reduction and what Gondrov's conjectures say in that setting and what we know so far. So to do that, I need to do a bit more explicitly introduce the coproduct and the notations from there. I think Danilo gave a definition of the coproduct, gave the exact formula for the coproduct. And I'm more interested in the co-bracket in the Lie algebra, so I'll write down something explicit for that.
So generated here, does that mean spanned as a vector space?
Yeah. Just being in phase. So to write down the formula, the precise formula for the co-bracket, it's helpful to use the integral notation.
Sorry, real quick. Does this mean that polylogarithms are automatically indecomposable? Is that automatic in some sense?
No, I mean take the projections of the polylogs to the.
Oh, I see. You just go to the indecomposables and then it could be zero.
Some things, yeah, like if you take product of log and project, it'll be 0, but
yeah.
No. So the notation that gets used here, if you're matching something that was called, is we'll treat like the motivic version of the iterated integral as some integral from A to B of some differential forms should correspond to that. can write the multiple polylogarithms, the analytic versions of them, in terms of integrals like this, and then view them as some version of these motivic iterated integrals. So formula, more precisely, is, depending on conventions, the sine minus 1 to the depth in here. And then it's integral from 0 to 1 of 1 over successive products of these indices. So the first one is 1 over product of all of the z's by some number of zeros. The total number of indices there is n1, the first index of the polylog. And you repeat this construction various times. So the second non-zero index is 1 over product from z2 to zr, followed by some number of zeros. And the total number of indices is n2. And you repeat this until 1 over zr, followed by some number of zeros. The total number there is nr. You have a way of writing the multiple polylogs as iterated integrals. So then it's easier to write down a formula for the coproduct on these integrals, and you can then work out what the coproduct and cobracket is on the polylogs from it. In Daniel's course, he wrote down the coproduct, and so projecting this to the Lie coalgebra, you get a formula for the cobracket, and that's what I want to use. The cobracket of integral like this. It's just sum over I less than j of taking the indices between I and j and removing them. So you take the integral from x0 to x1 to xi, make a cut there, then start from xj, continue to xn, and then the upper bound of the integral, and wedge that with then do the indices from I to j that you removed. And then you get the version on the polylogs just by using the integral representation. So maybe as an exercise now you could check the claims on Clement's mini course that
Is there a reason you didn't write the C there? It's just...
The semicolons?
that should be a semicolon, that should be a semicolon. Make them more distinct.
I think that's...
Better? Yes.
Do you also need to do the projection to the indecomposable?
I mean, everything here is already in the so it's I see the version in the coalgebra.
And this is different
Okay.
from...
If you see something that's an explicit product, then of course you send it to 0.
This is different from, I mean, this is only a part of the coproduct that Danilo drew on the board.
You take that and you just ask, well, what in there is obviously a product? And there's a bunch of terms that are clearly a product. You need to end up taking maybe, if you wrote it with a semicircular thing. You end up taking some piece that looks like that and saying, well, this integral is 1, this integral is 1, that's 1, that's 1, that's 1, and only this is left over on one side. So these are the things that survive from the coproduct into the cobracket.
The
indices go from 0 or from 1?
Then modulo whatever the obvious relations are that send various things to 0. As an example / exercise. Try and abbreviate as EX for example or exercise as you prefer. So with this formula you can check Glenon's claim that the cobracket of Ln is Ln minus 1 wedge log. But at some point you will need to use various identities like, either depending on definition or convention, the integral of length 0, weight 0 is 0, because in the Lie coalgebra we took the things of weight greater than 0 anyway, so anything weight 0 is just 0. So, you know, if you're taking terms like j equal to I plus 1, then you'll get something that doesn't have anything in here, say, and it's just 0. Then there's a few other things you would need to use as well. For example, that the integral even in the Hopf algebra that starts and ends with a, well, as an integral that's integral from a to that's 0. That's true even in the motivic Hopf algebra and certainly in the Lie coalgebra, at least if there's more, at least one thing there. And you'd also need to use, for example, that if you have a particular index repeated in here, say n times, you can write that as a product of weight 1 integral to some power over n factorial, and then when you project to the Lie coalgebra, that obviously vanishes if n is greater than 1. If you use things like that to check this formula, there's also a regularization step you need.
You said 0, 1 is 0. Is it even true that x0 to x1, like if you only have two things, is 0?
Right, so
anything, yeah. And then is it also 0 if you just have two neighboring things being the same? Instead of all n of them? Just
No. You need either all of them to be equal or you get some single thing. So for example, you're asking about something like x1. Asking about something like that. That's definitely non-zero. That's something you can put to some change value. That's like 1 or 1, x maybe, whatever the change of variables is that makes that right. And then it's just generally non-zero. I think to check this one, you also need to use some regularization step in a sense. You need to do this to work with the co-product in general. The weight 1 integral, like general parameters, is the difference of two logs. And if you see 0 appearing in here, so it's like integral of 0 to 0 to 1 or something, or 0 xx, you might see when doing these computations. You set the log to be 0, but this is like a minor point. And the thing to note with this computation that Clement mentioned is the code bracket of something of depth 1 has a piece that lands in weight n, n minus 1, where the piece that lands in weight 1 generically, the co-product is going to land in wedges of any possible combination of pieces. So as another exercise / example, you can check Li3, 1 of x, y. I won't write out the full formula, but it's a piece of the form weight 3 wedge weight 1, plus very explicitly Li2 of xy wedge Li2 of y. In particular, it has this piece that's in weight 2 wedge weight 2 and is non-zero. So there is absolutely no way you could write this as a combination of depth of n things, because the would not be able to produce this contribution. The corollary E31 of xy cannot be a sum of any number of Li4 terms. So it's not possible to make the co-bracket match. So if I introduce here the notation for the truncated version of the co-bracket, I'll write that with a bar over the top. By that I mean take the co-bracket and orphaned out by the weight 1 piece. Just whenever you see terms involving weight 1 here, just send them to 0. So then you see from this example, this truncated co-bracket would detect when something can't have depth 1. And Kontrov then conjectures not only does it, when it can't have depth 1, it detects exactly when its depth is 1. So there's a very special case of Kontrov's depth conjecture. Conjecture would essentially say the kernel of this truncated co-bracket is exactly depth 1 polylogs. I didn't introduce any notation for that.
L earlier. You called L the. Oh no, sorry, that was something.
That was for the.
Yeah.
That was for all of them. I don't want to use notation for depth filtration. I'll just write depth 1. I think that's clear enough. So then, this conjecture and an extension I will mention at the end is somehow like motivation for a lot of work I'm doing. But I'd like to just go through now some examples of what happens in weight 2, weight 3, and weight 4 with this conjecture, just for the background and explanation. So are there any questions up to that point?
Equal to is like the right hand side would be like the thing, everything that's spanned by. I mean, you mod out by C1 and you get out that the kernel is C1. I'm not quite sure I understand the conjecture.
Maybe precisely. So I take f to be some combination of multiple polylogs, so some coefficients, I, e, some indices, ni, some arguments, zi, just a general combination of multiple polylogs of very easiest to take a fixed weight.
Is it sort of saying anything of higher depth cannot be expressed in terms of depth 1? Is that what the conjecture is saying? Okay.
Yeah. Anything of high depth in what I mean, you can have things that look like they are higher depth, but could be written in terms of depth 1. So there's some subtlety there. But
I see.
More precisely, if I take f as some combination of multiple polylogs, whatever arguments, whatever indices you want, then the vanishing of this truncated code bracket is equivalent to there existing some combination usually in what was.
Yeah, okay, I get it.
That is equal to f.
Yeah. Okay.
So you take some arbitrary combination. If the code bracket vanishes, you should be able to find some linear combination of depth 1 things that equals your original expression up to polylog functional equations and identities and so on.
Yeah.
We'll go through some more precise examples in a moment. So what does this say in weight 2 and weight 3, just for simplicity to start with? Well, as another exercise or example, you can check that the truncated code bracket applied to Li1, 1 of xy is equal to 0. And the truncated code bracket applied to Li1, of x, y, z is 0. Just for the simple reason there's no space for a C2 wedge, C2 or higher part. Controlled conjecture in this case would say both of these things should be expressible in terms of depth 1. I can even give you an explicit example for the explicit formula for the first one. I'll even do it on the level of analytic functions. So Li11 of xy is equal to Li2 of y x minus 1 by 1 minus y minus Li2 y over y minus 1 minus Li2 of xy. So I'm saying this even holds true, like as power series. You can check using the series definition from earlier that this is an equality of Taylor series in region, I think. Less than 1, xy less than 1. So in that region, this is just an equality of Taylor series. And then you can check it even works on the motivic level. So that's the example of what control would say. You can take any linear combination of polylogs where the co-bracket vanishes and find an equivalent expression in terms of depth 1. And then for the Li111 example, it's a bit more complicated to write down, so I won't do it, but there is a combination of, I think, 8 Li3 terms that it's equal to, at least modulo products. The arguments are something like things like 1 minus xyz divided by xy 1 minus z, and then things of that form. Then it's a combination of 8 terms like that and some products.
Stephen, does this construct make any conjectures about the kind of arguments you need for it?
Not really, no. I mean, from the co-bracket you would see various pieces that look like Li n-1 of something, wedge log of something, and you can maybe try to combine those to get it, to have some guess on what the arguments should be. But there's really no particular prediction. Like, that's somehow the hard part of finding these depth reductions. You have no idea what the arguments necessarily could involve. There's a chance you would need to introduce completely new irreducible factors somewhere that just happen to cancel when you take particular linear combinations, because you need to see something, that factor appearing in 1 minus the argument somewhere later. So there's no good prediction. No.
But are they always rational?
That would be the conjecture, I guess, part of the conjecture, that you should be able to find arguments from the same field.
Because otherwise you would be extending the field,
yeah. So, I mean, there's some levels of subtlety here. Like, you can look at the conjecture over some algebraically closed field where you have roots of polynomials already, and you can show some things there. Like, as part of the story of the Steinberg module and polylogs, in a sort of precursor to that, we had a way of showing that you could easily get any particular term in the co-bracket just like as an isolated piece by taking a combination of distribution relations plugged into polylogs in a certain way. Then that necessarily needs like nth roots of things appearing, and it's a bit... So in principle, the conjecture, or at least the version we would want to show, is with rational function arguments of the same variables you take.
And in practice, are those arguments always like morally linear in all the variables, or do you get like way more complicated polynomials?
You can get very complicated things. Like as an example, I'll come to linear polynomials. There's definitely places where you see polynomials squared and things like that, and high degree polynomials appearing. It gets quite complicated. Go to this.
Is the co-product in some sense graded with the depth? Like if you have something of depth n and you take the co-product, do you get any kind of restrictions on what?
It just behaves nicely in that sense.
Because then, I mean, if you have something of depth 2, of course, mod C1 of mod depth 1, you would get no co-product, right?
Indeed, so
And
there is
so
some
that means
structure
now
like
you can write everything of depth 2 in terms of depth 1, is that what it means?
Also, Peter, C1 is weight 1, not depth 1.
Ah,
weight one, sorry.
I think that's my entire confusion the entire time. Thank you for clarifying that.
You know, there's some structure going on like that. You get the co-product not respecting the depth in a certain way. So the co-product of something of depth D will involve a piece of depth D wedge weight 1, and then all of the other contributions should be depth less than D, wedge depth less than D in a way that combines to be the original depth you started with. So it behaves nicely in that sense. Okay, maybe just for some historical context as well. It's like both of these reductions of your general polylog of depth 2 and depth 3, like weight 2 and weight 3 to depth 1 are known for, well, certainly they appear in like Lewin's textbook on polylogs, but presumably go back a lot further than that. But they were really only popularized very recently when Goncharov realized what the depth conjecture would be saying in this case, and then when Gonzaga essentially was challenged to find this identity and found it overnight. And if this is well known and dates back centuries, decades or centuries, everybody should know about it. And it seems very few people did at the time, so to really popularize it and just make it well known.
So when you do it in this general symbolic level within this function field with x and y, when I want to specialize to particular numbers, right, I could hit a point where some of these arguments are infinite or not well defined. When I plug in y equal 1 or something in here.
There is some way you can precisely do like degenerations to speed 0 or 1 infinity in various ways.
Okay.
I mean, as part of this setup, I can try to explain a bit more precisely later if there's time. But there is a precise procedure to degenerate a polylog identity on a motivic level to some way we're going to 0, 1, infinity, something else, and deal with the terms where you get, say, log of infinity or whatever.
So it's enough to prove depth reduction for a function field, and then it follows form.
And then, any sort of identity you'd get between numbers or between polylogs of numbers that should satisfy similar depth reductions, you can extract from this. So then I continue with the story in weight 4. Already had the example here showing that in weight 4 you really do need a depth 2 function, Lie3, 1. You can't write in terms of depth 1, so is really a new function that you need. The fact to go along with that is you can express every weight 4 multiple polylog via Lie3, 1 and Lie4. So these two things are enough. That on its own is a little lemma or theorem you have to prove. But in general, there are some known reductions that will take you from depth n to depth n minus 2. So you would easily get the Lie3, 1 thing, Lie2, 2 and Lie1, 3 as the basic ingredients. And then you can reduce those other ones to Lie3, 1. So just as the factor will take Lie3, 1 and Lie4 as the only things you need.
Could you remind us who did this in this weight 4 case, this reduction that I think he has become famous recently?
If you mean the president of Romania, do you mean the president of Romania, or do you mean independently Francis Brown? I mean, Francis does have the rep theory set up that I guess the president of Romania got the weight for reduction first. It's buried somewhere else in Lou, and I sort of wouldn't be surprised if somehow it was known a bit earlier on as well. But he has the setup that works for general depth n to depth n minus 2. So for example, if I got the first name correct. So then, in weight 4, maybe the question you want to ask now is, when can you concoct a combination of polylogs, you know, Lie 3-1s and Lie 4s that has vanishing co-bracket? What are sort of the basic things you need? So, okay, let me, for simplicity, introduce notation for a certain change of variables. I'm going to write Lie 3-1 with a twiddle to be Lie 3-1 of x over y comma y. So the co-bracket of Lie 3-1 twiddle is, the truncated co-bracket is Lie 2 of x, like Lie 2 of y. In particular, you now have a nice clean separation. The x's are in one function, the y's are in another function. It becomes a bit more obvious how to concoct combinations where the co-bracket vanishes. So the co-bracket will vanish if you substitute x to be a Lie 2 functional equation. So you take a combination of Lie 3-1s of x, y, where the x's form a dialog identity, and then that will just vanish naturally. So if we recall the two simple dialog identities that the command mentioned, that Lie 2 of x plus Lie 2 of 1 minus x, at least the mod products version is equal to 0, and Lie 2 of x plus Lie 2 of 1 over x is equal to 0. Again, the mod products version. Then we expect taking the combination Lie 3-1 with similar arguments, changing all the Lie 2s to Lie 3-1 of something comma y, should be depth 1. And indeed, these two conjectures are true. So the theorem is that there is an explicit linear combination of Lie 4 terms you can plug in here and a different one here that agrees with the Lie 3-1 terms. I think one of those identities is due to Don Zagier, the other I think is due to Herbert Gangle, but both appear in one of Herbert's papers. So there's not a clean version I can point to that, you know, it's written down by Don here. And in this this kind of very simple case, the idea is you can even do the calculations by hand and see roughly you need to have Lie-4 terms of a certain shape and just match them up really by hand. This is about the maximum level of complexity you can get to by doing calculations by hand. At this point, after this, everything gets much more complicated. So these are the two sort of simple symmetries you get for Lie-3-1. The more interesting identity is when you take not just the dialog symmetries, but plug in the 5-term relation. So the 5-term relation for the dialog was this alternating sum of cross ratios of 4 points out of 5. That summed up to 0. And then applying the depth conjecture here would say Lie-3-1 if the same thing, a new variable, should reduce to depth 1. So then the good thing is this identity is true. This does reduce to depth 1. I don't want to say the unfortunate thing, but the thing that makes us realize how complicated the story is how long the resulting identity is and how much work it takes to find. You wrote it for I3-1, the integral, rather than I've done some change of variables, so just a few minutes here. And Z1 is Z5. So this combination of 5 Lie-3-1 terms where the code bracket vanishes is indeed equal to a combination of Lie-4 terms. There's, in sort of the minimal presentation, there's something like 122 of them. And the arguments involved are products of up to 4 cross ratios divided by 4 cross ratios. So it starts getting quite complicated. And originally this was found with some judicious use of computer experimentation and looking at what functions, what arguments are appearing in the code bracket and trying to reconstruct where they could come from in terms of Lie-4s. But still took some amount of judiciously identifying what potential new factors you would have to introduce and see what sort of arguments they then generate. More recently, we have a more conceptual understanding of this using the functional equations that Gontarov and Rudenko used to prove the Zegers conjecture on zeta F4, and the more recent quadrangular polylogs that Rudenko and Andrei Matviakin developed to get these functional equations in all weights. The idea in those cases is to take to take this nice polylog identity relating some depth 2 terms and depth 1 terms and to specialize it in lots of ways. by doing lots of specializations, you can produce some simpler identities like a symmetry relating. To get some symmetry like relating Li3-1 of xy and Li3-1 of 1 minus x, 1 over 1 minus y as a starting point. You can get some symmetries like this to play against each other in order to produce, well, the Li3-1 symmetries, where you just have an x going to 1 minus x and y is fixed. And then from this you can again derive some nice identity relating two copies of Li3-1 of the 5 term and find some extra symmetry there. You can play against itself in order to deduce more conceptual results.
Is there a tilde on the second Li3-1 or?
So yes. So, I mean, roughly this is all I wanted to say for the weight 4 story. If there was time at the end, which there seems not to be, I would have mentioned something about the weight 6 story, but feel free to ask me. Yeah, ask me later.
Yeah, are there any questions?
I just want to make sure this relation has nothing to do with this distribution relations.
This one, I mean,
Yeah, this kind of perhaps one reduction has anything to do with the distribution relation?
not really, no. I mean, in a sense, the x1 over x looks kind of like distribution for power being -1, but it's really not. Like the distribution relation for depth 2 is something like let's do x and y. X to the n is some variable, y to the n is another variable. You sum over all choices of roots of some capital X and capital Y, and you get, I can never remember what the coefficient is, but then you get some multiple of the function evaluated as capital X, capital Y. So you could maybe think of that as some depth reduction if you move everything to the other side and say it reduces to depth 0, but no, it's really nothing to do with that.
But is it a short question?
Yeah. So the question is, weight 6?
No, that's not it. maybe in the break for you. If you are leaving to, you have a short question?
Yeah.
Yeah, sure.
Just in the spirit of the talks yesterday, so when we were taught how to, this polylog story maps to the Steinberg, tensor Steinberg. Is there any interpretation of the Sohl-Goncharoff depth reduction in the Steinberg side of things?
Well, we should probably try to look at that more carefully, because currently all of these identities were either conceptually understood or conceptually derived using these quadrangular polylogs. This gives some nice source of identities that you can degenerate and specialize. We really ought to look at this all again, including the weight 6 case, which is much more complicated, and try to understand it using, say, the identities that were coming from H1, GL, and these coefficients in Steinberg into the polylogs. Try to understand it from the identities that were coming from this map mentioned in Ismail's talk, because this is like a nice new class of geometrically arising polylog identities, and specializing them would probably be a way to more generally tackle this depth reduction story, and we need to do that.
So we'll post on questions.
Just a yes, no question with that?
Are you able to? If you are leaving today, don't forget to check out before 10 a.m. So do it in the break right now.
Ask the front desk and they said 11. I'll ask the front desk just now and they said 11.
Well, probably good to do it now. We'll resume at 10:05. I think it'd be nice to, I think we forgot to do this earlier, but I think it would be nice after the next talk to do a little picture with all the participants that are still here. And let's thank Stephen again.